Hello, this is video log entry 120 and curly. It is about 11 a.m. CST. I was just kind of thinking about quantum physics again. Just because, again, I'm kind of trying to somewhat not recreate, maybe look at the perspective of the physicists from like the 1900s when they were creating quantum field theory and whatnot. Well, mainly from quantum physics to a quantum field theory, because the wave nature of particles in general and whatnot. And I was looking at one thing I didn't really understand was spin, and spin was actually quote unquote found by the Stern-Gerlach experiment. Basically, they had these like silver material or something, and these atoms. Basically, so the magnetic field tends to be affected by the angular momentum of a electron's orbital movement, because it's moving through space, right? So a moving particle also creates a moving particle, or electron creates a magnetic field, and or current. You can think of it as current or whatever. Oh, I mean, current is pertaining to actual electricity within wires and whatnot. It's not really the same thing. It's just still just moving particles within the electromagnetic field produce a magnetic field as well, as you can see. So I was thinking, I was also thinking about like how the parity of fields and whatnot, and these parity of fields tend to be orthogonal. You can think about the electromagnetic waves and how they interact with each other. And what the Stern-Gerlach experiment actually figured out was like, oh, wait a second, there's no orbital angular momentum, but it still happens to have two orientations with the magnetic field. Supposedly, I don't know how I didn't really look into the Stern-Gerlach experiment as much as I'd like to, but supposedly that's what they found, is that's how they found spin in electrons and whatnot. And I'm not sure, do all particles have spin? I don't know. That's I'm assuming they all have spin, just because of my theory is they're so confused about it. I think the reason why they're confused is because of how they depict spin. They depict an orbiting electron. Now that's interesting to think about, but they're also still thinking about it from the particle's perspective and not the field, since everything is fields now, and quote unquote information. You can think about information imposed on a field in one direction, but you can also think about information imposed on the field in the other direction. And that could also be a explanation of why physicists tend to be confused about what spin is, because they're still thinking about spinning particles as opposed to it just being information imposed on a field in different orientations. Now, of course, I wouldn't know because I'm not a physicist, but from my perspective, especially from a information theory perspective, it seems to explain it pretty well. The reason why they have integer numbers is because, what's a good way to think of it actually? Do these particles with spin, do they seem to exhibit fractions, right? They exhibit fractions, and I wouldn't be able to explain why. Again, these are numbers. I don't really look at the numbers as much as I should. I usually look at these symbols and the abstractions pertaining to those numbers. So I'm not 100% sure how many spins does an electron have. Maybe this is just like stream of consciousness stuff. I was just writing things down. I was looking at other things as well, like I also look at the velocity of waves from a impulse perspective, which isn't, I mean, again, you can think of it mathematically. Yes, you can think of it mathematically and rederive it from a very rigorous mathematical standpoint through partial differential equations and think about it as a mechanical wave, but I like to think about things intuitively and kind of parsing through. What's a good word for that? Not parsing through. Just flying over the mathematical structures. So, I mean, it tends to work with my brain pretty well. So I tend to, I'm more of an intuitive, I guess would be the good way to say it. Yeah, electrons have two possible spin states, plus 1/2. I don't know how they got these numbers. Again, they're plus 1/2 minus 1/2. They're polar to each other. They negate each other, and you can think of information, the imposition. Imposition, is that even a word? The imposition on information on a field. Posing something or being imposed. Yeah, imposition of information on a field, and the way sure, you can think about the imposition of information on a field in different angles, of course, but if you think about the imposition of information on a field from different angles, then that particle is no longer standing. But at the same time, we're looking, when we think about spin, we're looking at the axis orthogonal to the field itself. This is all from a two-dimensional perspective, yes, because it's good to start off from simple assumptions and build up from there, and then you can create a nice framework to kind of encapsulate the more complex systems and whatnot. So I think I don't know if people are still confused about that, but that's a really good way to think about spin. I think they're holding on to the conception of a particle still. I think that's the issue, is that they're holding on to the conception of particles, and so they feel like they have to I think once people let go of Newton's perspective of everything being a billiard ball, everything will just kind of fall into place if you just let go of it and just think of everything as waves and information, or just information and its field counterpart. Yes, I mean, we can talk about infinitesimals and all that, but I'm kind of going over a lot of the quote unquote rigor that can be understood through probably real analysis. And there were other things I was looking at. I was looking at the Schrodinger equation, of course, and I still don't really have I can only think of one good way to think of it. I mean, of course, the Schrodinger equation tends to encapsulate two pieces of information. One being like the position of again, you have to think about it in people like to think of it as a packet, a wave packet, a quanta, right? So you have the wave, right, and then you have the wave moving in space, but then you also have that's the position of the actual packet, so that has to be quantified within the Schrodinger equation. But then you also have to think about the packet's phase state. You can think of it as a phase state because if you think about wave packets and its dynamics, you can have these troughs kind of moving through in this space interval, and it's a good way for when you have two waves in the same spot, like you just think of two electrons, wave packets in the same place, then you can impose the understanding of the phase that these packets are in to understand how they interfere with each other and all that. Of course, you can think of it as it being misaligned, but it's easier to think of them like right in the same space from a two-dimensional perspective, because you're thinking about the energy, and then for me, I'm thinking, I guess, so one-dimensional spatial perspective, and then the other dimension is quote-unquote energy or information, whatever you want to call it, and that's why they have a complex Schrodinger equation to encapsulate not only the position of the wave packet, but the quote-unquote, you can think of it as the state or the phase that it's in. Of course, if you understand waves to any degree, you kind of understand it. It can seem complicated, but if you think about waves a lot, it's not. It's like yeah. So that's why they make it a complex number, because that quote unquote number or input, the state of the Schrodinger equation, or whatever you want to call it, it's not as profound as people think. It's really just a way of encoding information conveniently, because then you can actually you can take the magnitude of this wave squared to come up with a probability distribution to find the quote unquote, well, just to understand where it can be before an observer looks at it, because once any kind of, it's not just a human observer, it's any observer. It can be it could also be like, it could be anything. Like, so humans like to think that they're like the center of the world, so they believe that it's their brains that are coming up, but it's more than their brains. It's really more than their brains. It's everything. It's any kind of system. Like, my coffee pot is an observer of me, and I'm an observer of it. Like, it's not just our brains. We're not that special, unfortunately. I know, like, the human mind tends to be well, you can actually look at the evolution of like the humans and whatnot, and how they actually thought of things. They were always centric, right? They always believed in, like, if you look at astronomy, they had a geocentric model, thinking that they were the center of the universe, but no, they happened to be, within it happened to be heliocentric. We were going around the sun as opposed to the sun going around us. Not only that, I think there was probably a time in which we still believed that the solar system was the center of the universe itself. Obviously, that's not the case either. Oh, we should also think of like humans as well. Like, humans aren't the center of the universe either. So, yeah. So I mean, like, it's just like, I think it's just how people think about these things. It doesn't click in. They're just taking the wrong approach, and they're taking things from old conceptual frameworks that aren't necessarily working with how reality is now and how we perceive it. There's some things we just have to let go of. One of them is thinking about the world as a billiard ball. It's a set of billiard balls, or particles, and any kind of information as billiard balls. It worked for a while, but it doesn't work anymore. Yeah, so the Stern-Gerlach experiment seems interesting. Let me see the details of this experiment, just to understand why spin had to be encapsulated in this. Yep, exactly. So silver atoms. These were silver atoms through an inhomogeneous magnetic field, and being deflected up or down depending on their spin. So again, I was talking about this too, how it again, it's in a magnetic field too. So these particles have two states, right? These particles, again, you can think of it from a information standpoint. And of course, like, this Stern-Gerlach experiment can be seen from a two-dimensional space perspective, of course. But you can still, these particles probably aligned with the magnetic field, I think. I don't know how that works, because they can. That's the more interesting part, is that, you would have to think about, like, three-dimensional space, or the magnetic field is three-dimensional and all that, and how that's a little bit more interesting to think about. But from a one-dimensional perspective, it makes sense. From a three-dimensional perspective, of course, you can think about again, you can impose a fourth dimension for spin, and that's hard to think about, other than the fact that still you're adding a new dimension, and it happens, the imposition of information even within, from that perspective. This sounds crazy, but it's still up or down. So you can still impose, like, no matter how many dimensions you add, it's still up or down, which is why you have polarity and one half, and I don't know how they came up with those numbers. I'm not going to try to understand that yet, because again, I'm not looking at all the details. I'm just looking at how to approach it from a different standpoint, and that's like the best explanation I could come up with now. And this Stern-Gerlach experiment does explain my theory just as well as anybody thinking about spinning particles. I just think it's absurd that people think that spinning particles are a thing, because if they were spinning particles, they would also create a rippling effect like the Earth and space-time, but it does not. It does not. There's no ripple effect. There's no fucking ripple effect. So why do people think about it as spin? Of course they have to think about it as spin because they still see it's again, they're not letting go of the idea of particles. Maybe people do know that, but they like to make it seem more profound than it is to confuse students even more. Maybe just be like, oh, this is confusing, guys. Don't get into physics. Nobody understands why particles have spin. It's like, okay, yeah, sure, whatever. I was also looking at like spin orbit coupling. Spin orbit coupling. I haven't. I found a video on that actually, and there's a video by Parth G, and I don't know what that actually means. Oh, it has to do with the fine structure. Oh, okay. So spin orbit coupling. What else was I looking at? I was talking about like squaring the wave function and all that, and like from a measurement standpoint, it makes sense, but I'd prefer not to really think about it too hard because, like, my manager's calling me probably because of my paycheck. Yeah, so I'll answer that in a second. Well, my old manager, I don't work for him anymore, but yeah, so I understand. It's again a complex nature, quote unquote complex. It's just a form of measurement. Same thing. I'm going to keep it as simple as we square the wave function because it maps it to a probability distribution that happens to well, it also like the probability distribution. There's another thing is like the Schrodinger equation. It has to be normalized, right? So when you square it, it has to have the area be 1 because the probability distribution is like the whole area being 1. Because you think about, well, if you guys know anything about bell curves or anything like that, of course that has to be the case. It's just how it's mapping decimals to percentages and whatnot, I guess, if you want to think of it like that. I'm going to pause for a little bit. I'm probably going to make a part 2 just to see if anything else comes up. I talk to my boss really quick. Bye.